thought I'd put this slide back up just to give us a refresher, particularly after the discussions that we had just before the break. And I think the main thing that I haven't really got into enough, definitely came out in the discussion, was exactly what this coroutine frame really is. Mostly because you can't really see it. But if you think of it as a class that has some methods on it, in like a superset way, like a lambda translates to a struct with a call operator, well, this translates to a class with several methods and some other machinery as well. But the promise type is part of the state of that class. So are all of the member variables. Again, in the same way that local variables in a lambda become member variables in the struct it translates to, local variables in a coroutine become member variables of this conceptual coroutine frame class.
You mean in the same way that capture variables become members of the lambda?
Yes. You can tell the ibuprofen's wearing off. Thank you for that clarification. Oh, this should help. Thank you. 1 second. Much better. Right. No, trying to get ahead of it. Yes, I think that can help. That's pretty much what John said helped him, actually. And then your interface to, not interface, it's the wrong word. Your way to get at the coroutine frame is with the coroutine handle. And from the coroutine handle, you can get the promise, which is part of the frame. So as well as the local variables in there, you've got the promise type in there as well. So I know I said that before. I think it's worth restating it again now before we dig into these a bit more. Any other questions at this level before we carry on? Dave.
For my own clarity, the task class generator has a promise type and the coroutine frame has a promise instance.
Yes. Yep, that's correct. So to repeat that, the task or generator class has the promise type, or at least a forward reference to it, and the coroutine frame has the promise instance. I think was what you said. You can get to that instance through the coroutine handle. We'll see that happening. So really, this is mostly just an interface to the state we've got going on up there. Right. Let's go back to the code. So we looked from this side. Now let's flip to the underbelly. If I can remember where they all are. So let's start at, not there, I moved it to here. Here. So build task. So this is what the top level coroutines, the ones that are doing the deserializing and dependency stuff, are returning. So you can see we've got the complete definition of the promise type here. Again, you don't have to put it in here. You just have to have something that says promise underscore type that is either type alias or this or a forward reference. But this is a common, simple way to do it. So remember, the state from here will actually be located in the coroutine frame. Keep emphasizing that. So you can see there's a bit of state at the top. Then we've got our methods here. So maybe the first thing to walk through is the getReturn object. Now we can see that. You might remember way back when I first showed that earlier slide that I said this is how the coroutine machinery gets hold of our task object in the first place. It calls getReturn object, and that's going to return, in this case, our build task. And it's returning the handle, the coroutine handle. So it's passing the coroutine handle to the build task, which you can get using that handle from promise helper. From the promise you can get to the handle, from the handle you can get to the promise. I only ever tend to see the handle from promise here. Most of the time it's the other way around. That make sense? Then we've got our initial suspend. So in this case, it's suspend never. That means that when our coroutine starts, it's just going to start executing the code in the coroutine body straight away until it hits the first suspend point. Marshall.
Initial, this is a nit, okay? But I want to know if it's specified that way or you just forgot no except. Initial
yes.
suspend is not no except, and final suspend is.
I
It's
believe that
supposed
was
to be
just
the
a.
same, or they're
I
supposed to
think
be
it's supposed to be the same.
Okay, thank you.
You'll probably see lots of those things. If you think it might be significant, do ask,
Yes,
and I can
right.
verify
That's
whether
all
it
I
should be that
wanted
way or
to
not.
know.
Yeah.
Is
Yeah.
there a reason that they're different, other than
No,
slightly? Okay.
absolutely. It does run, but yeah. So one thing you'll notice when we've got auto return types here, but the return type is actually suspend never or suspend always. That means that the compiler can check that at compile time.
Well, the final suspend has to be no except. If you remove no except from a final suspend, it won't compile.
That's probably true. Maybe that's why it's that way. But it should also be on the initial suspend as well. No reason for it not to be.
I think the initial suspend is allowed to throw an exception, and it will propagate out of the function call, whereas final suspend doesn't work.
Okay.
Okay, good.
So they're specified.
Thanks for the clarification.
They're specified differently. Okay.
So maybe that is why I did it that way.
The standard. If you do anything less, it just won't compile it. You can always do more.
Got it. Thank you.
That sounds right. Yeah, that's details I've forgotten somewhere in the midst of time. So thanks for that. So what was I saying? Yeah. So because we're returning the types here, we can actually work out whether to initially suspend that compile time. You can return because these are our waiters. We'll look at waiters in a minute. You can return an awaiter that will return at runtime, whether it should initially suspend or not. And there are good use cases for that. But here, and most of the time, to be fair, you'll return one of those two. And final suspend will usually be suspend always, for the reasons we discussed earlier. So that's something you don't generally have to worry about too much. And then we've got return value. So when we hit that co-return with our final built object, it will get passed to return underscore value. Remember, if you don't have return underscore value, you can have return underscore void instead, if you don't have a return type. Dave?
Can return underscore value be overloaded?
Yes, I believe so.
In the example in CPQ reference, I think it's a template function, so you can only also overload it. So the function template.
Like all of these are called by the compiler just emitting a function call, and so anything you can do for a function call will work. You can overload them, you can make them templates, etc.
I mean, just the reason why it's a little bit weird is when I think of like returning something over and over again. I think in my mind they're returning the same type, but not true with coroutines. Coroutines.
Well, you should only have one co-return. We can have multiple co-returns. It'll only hit one of them, and then that's the end. But which one it hits may return a different type.
Right. Yeah. It'd be like, if some expression co-return a string and otherwise
Yeah,
co-return.
exactly.
Just imagine you return std any from your function, or you return a type that can be constructed from anything. Then you can return anything.
Timo?
I have a question about the return underscore value.
Yeah.
So presumably, like the way I understand this is that the compiler will call this function and will pass in a reference to the thing that it's supposed to return, right?
The argument of the co-return.
So the
Yeah.
new underscore object, the argument of the return value function, that's going to be the thing that the compiler will tell you, please return this when it calls you there, right?
Yeah.
Now, it gets assigned to this object member.
Mhm.
How is that connected to anything? I just see a member declaration, put f object equals null pointer. Where does it actually return that to anywhere else?
Ah.
Like, how is this object connected to anything?
So good question. We will come on to see that. But what I want to note right now is that obviously obj here is part of the promise type. which lives in the coroutine frame. So we've squirreled it away in our coroutine state, which later we can get to from our build task.
Okay.
And so we'll need to ask for it.
Okay, so the way it looks to me now is that the compiler is asking us to return a value, and then we just assign the value to a member that's not used anywhere else, and that's the end of the story. That's what it looks like.
Well, it's a
Also
puzzle
on the
bar,
screen.
so it can be used. We'll see.
Yeah.
Hopefully when we scroll down, we'll see.
Okay.
Think of the promise type as a staging area for lots of this stuff.
Okay.
Yeah, so suspend that fault for the moment, I think. I've got more, don't worry. And in fact, the other one up here, unmet dependencies, according to the comment, that's going to come from the awaiter. So we'll see that as well in a bit. Now, all of these methods, well, interestingly, they're grayed out because C-line in this case, I think, thinks that they're not used because none of our code ever calls these, all called by the compiler. So all of those grey functions are the ones that we have to provide to satisfy the compiling machinery to make this a coroutine. And if we don't, except for the optional ones, then we should get a compiler error.
Yeah, don't worry, the grayed out stuff, you're going to fix that.
Real-time updates. Okay, so that's the promise type for now. I'm sure we'll come back to it. By the way, this static count up here, that's just simply so I can keep track of how many build tasks we have live at any moment. You can see we're just incrementing it in the constructor. And that's the thing we're asserting on right at the end, just to verify that we've cleaned them all up. That's all that's there for. That's just for demo code, not really a production thing. Okay, so that's the promise type. But that's part of our task object, task class, which you can see has exactly one state variable, which is the coroutine handle. You can have other state, but you have to be careful with it because these things may be copied or moved around. Generally, try to make these at least non-copyable because of that single ownership problem. If you do want to make them movable, so I've got a move constructor here. I can't do equals default because we actually need to clear the coroutine handle from the outgoing build task. Otherwise, I'll both try to destroy them. So it's just simpler if you don't make them movable in the first place, but I needed to here. And then we've got our main constructor, which takes the coroutine handle. So that's what getReturnObject is calling up there. Okay, so we've got our build task. The destructor of the build task is where we're going to need to do our lifetime management of the coroutine handle. So if we have one, we call destroy on it. You could build some sort of reference counted implementation on top of this. I don't think it's a good thing to do, but there may be a use case for it. David, yes?
I don't understand why you'd want to have more than one copy of build task.
Well, you don't, for this reason. But you may want to give it out to different places. So we'll see how that becomes a problem in a bit.
Wait, there's a vector of these, and so they have to be movable. I mean,
That was the reason I had to add that, yeah.
I get like move only build task, but if you have move only, then why would count ever be?
I know, because count is static. So every instance of build task will increment that, not just this one.
Okay.
Does that answer your question? You still look a bit puzzled.
Yeah, I guess I'm still puzzled. So count is static,
Yes.
and you're saying that you can only have one of those handles at a given time?
No.
Or a coroutine, or instance of a coroutine.
Yeah. For a given coroutine and a given coroutine handle, there should be exactly one build task managing it.
But if you have multiple coroutines,
They will all have their own build tasks with their own handles. Yes. And in fact, that's exactly what we will have, because we're going to store them all in that vector. Yeah, Ben.
It looks strange to me in the destructor that you're explicitly calling destroy when the handle is about to be destructed.
The handle's not about to be destructed. So the coroutine handle is not an RAI object. If we don't do that here, it's going to leak. So the task is responsible for managing.
Coroutine handle is a member variable of build task, and build tasks being destroyed, but coroutine handle isn't.
The coroutine handle object is going to have its destructor called, but it's trivially destructible. It's a thin
Oh,
wrapper.
yes, sorry, yeah, good clarification. The coroutine handle is yes. If you think of it just as a pointer. Okay. Is that making sense? It's worth making sure we get this right.
For a moment.
Sorry?
Could you scroll it down to the destructor for just a moment?
Oh yeah, sorry, that's gone off. Yep. Also, I've got the logging in there as well and the count. It's actually conceptually very simple. But we need to get this stuff right, because this is the memory management, resource management side of it. The build task effectively owns the coroutine handle, which owns the coroutine frame. Think of it that way. Any other questions on that? Okay.
Another question?
Yeah.
So for, I guess, a common user who, wants to do like the simplest possible things with coroutines, how much of this do they need to explicitly implement versus using some established utility class?
Depends what you mean by established utility class. So that's what we don't have in the standard library at the moment. They will be coming. We've heard that the generator version, at least, should be coming in 23.
Yeah, so standard, if you look at standard generator, it does 75% of this boilerplate stuff for you or more, maybe more. It depends on your use case a little bit, obviously, and how much customization, but if you wanted to turn sort of a simple function into an actual coroutine, then you shouldn't have to write most of this stuff. It's really the idea.
Okay. If you're using coroutines to lazily produce values, then you can use the generator and you'll be fine.
Yep.
If you're using coroutines to implement asynchronous I/O,
Well, that's different. Yeah.
there's
Yep.
usually more cooperation needed with the runtime, and so you'll probably have to do more of this. Both Folly has a pretty good coroutines library, and there's also cppcoro, and those will provide definitions for types and promises and so on, but they might not provide your I/O loop.
Okay, thank you.
So who here remembers the book Accelerated C++? So about half. What was the main revolution of that book, apart from just being particularly well written? The thing that sort of did different to most of the ones that came before was that it started with the high level abstractions and then sort of worked back and often didn't get to the low level stuff. So rather than teaching char star strings, it taught string. So when we actually get good standard library support for at least generator and hopefully some async stuff as well, then we will probably start these sorts of presentations with, here's how you do it with the standard library. Oh, and if you need some more advanced stuff, look under the hood. I think in this case, though, you're probably going to want to look under the hood sooner anyway. Maybe not right at the start. I think it is going to be valid to start with the simpler examples, but there are going to be so many cases you're going to need to customize it. And also just understanding what the flow of these things is, that it's just worth knowing what's going on behind the scenes. So, are we okay for the resource management?
What's the rest of the task?
That's what we're going to get onto.
Okay.
Are you doing anything with count apart from incrementing and decrementing?
Nope. It's just purely so that we can assert on it at the end.
Leave it out because you never inspect it.
It does in vain.
Yeah, yeah.
There's a technical
Ah,
limit of 0.
okay.
Yeah, so that's the thing I showed right at the start, down here.
Okay.
Yeah.
That's public. Oh, okay.
Yeah. So it's purely for purpose of this demo. It's not something you would normally put in there at all. Okay, so I'll notice that for my logging, I'm logging the destruction of the build task itself, but also whether we actually had a handle on deleting that. most of the rest of it, you'll see, is just calling through the handle to the promise to get some state from there. You might want to pull some of it back to work on locally, but as I say, you can get some problems with lifetime management. If you're not non-copyable and non-movable, or you're going to handle all of that, then you might be okay, but this is probably the safest way. We're just reaching into the promise and dealing with the state there. So we've got our ID string that we can also set here, and unmet dependencies. We've also got get built object. We will. Well, that was what we were going to come back to, wasn't it? So I think this was the question that Tim was asking. What happens to that object? We're just setting it there and then leaving it. So when we do co-return, it calls return value, sets that object in the promise. The build task gives access to it with the get build object method. So it's just normal code at this point. You'll be pleased to know. So whoever's holding the task can call get build object and get the object out. That's it. I think the only other thing to look at here is probably these ones. So resume. This is the interface that the user of this coroutine is going to have. When they're ready to resume, they're going to call resume. That's then going to, if we are not ready, as in it's not complete, call resume on the coroutine handle and return whether the coroutine is finished. So it's just providing a little abstraction over the coroutine handle itself.
One question. What guarantees that you didn't check for done before calling resume? What guarantee do you have that done is not set before calling resume?
The dot done. So is ready.
Done was already set, then calling resume that you be.
Yeah, sorry, I think I skipped over. Is ready is just returning whether the coroutine is done. In fact, I probably should have put that here instead just to make it match up. They're both doing the same thing. So if we're already done, then we return false. Otherwise, we resume. And if after resuming we're now done, we return false. So after calling this, we'll know whether the coroutine is done or not. Make sense? And then the other method to look at here, set dependency. So this is when the calling code has an object that it thinks that this task is interested in. It will pass it in with the ID and the object. And that's then going to find the corresponding unmet dependency, which has in the promise type, and then call the setter on that. And that will then set it, write it into the object that's being built. Oh, and remove it from our unmet dependencies vector. So now we're starting to get into the mechanics of our problem, not just the coroutines themselves. So if I go back to here, I thought I did have another method called that, but the user can call get unmet dependencies and check whether it's empty. I thought I had a method on it to do that deliberately. And that's it, really. That's our complete build task. Hopefully that makes some sense as part of the puzzle. This is what we get back when we call one of those build functions.
Making more sense.
Okay. Well, hopefully that'll come around. But
I'm hoping.
at this point, as long as you understand the individual bits, then some things will connect up. All right. If we go back to main and into here, might make sense if we see some in action. So we've got the extra level of indirection with that batch build task, but ultimately we get our build tasks here, and we're going to iterate over them. So remember, the first time we call it, the things we requested, they're going to be loaded, and we'll get build tasks for them, which roughly corresponds to those builder types that we saw in the previous example, if you remember that. The things that stored the dependencies and the object itself. But now it's a coroutine. So we can ask it for the ID. We can ask if it's empty. I've left that as an exercise to the reader, how to handle that. So the data was missing, basically. And we can get the unmet dependencies. And now we're in the loop that's actually going to do something with that. So the first thing we're going to do is just loop through the unmet dependencies. I'm doing it backwards by index, because when we make one of those dependencies, we want to remove it from the vector and carry on iterating. So that was just a way to do that without copying them. So we'll get that. Look it up in the cache. This is very similar to the code we saw before. If it's in the cache, we'll call set dependency. We'll look at that in a minute, and remove it from the dependent tasks container, which is the one that just has a big map of everything that's depending on these different objects. Otherwise, we'll add it to our to load list for the next time around the loop. So we've got an object come in, it says I've got these dependencies. If some of them are missing, we're going to load them next time. Make sense so far? Having done that, and we'll come back to some bits, but having done that, if the dependencies are now all met, we can resume the task. Task.resume. We looked at that a moment ago. That just calls resume on the coroutine itself, unless it's already finished. If it returns false, and I'm not sure I like that convention, the Boolean. It's not very expressive. I can never remember whether that should return true or false, but if it returns false, it means that we completed. So we have our built object. We can get it with getBuiltObject. Remember, that was the thing that gives you access to what coroutine gave you. And now we can call setObject on it. Set dependency, set object, we'll look at in a moment. And then finally, if the dependencies are not empty, then we don't do any of that, and we will just add them to our dependent tasks container. Starting to feel the thin air again now. Okay. That's the end of the loop for the moment. And so we'll come back to the set objects and set dependency. But any questions about any of that? Yeah.
If we don't like task.resume returning the bool because we don't know what it actually means, we can change that function, right? Because it's a member function of the task object.
Yes, that's in our control. I've been meaning to put an enum in there or something instead. So where was? Oh yeah. So up here. We can choose to return something else. That's in our control. Absolutely. It's entirely my fault, I admit. Any other questions? Then let's dig in to set dependency, because it's a simpler one. It's actually mostly just doing this, calling set dependency on the dependent task. We'll obviously need to look at that as well. But if, having done that, the dependent task is now complete. Remember, we had this similar situation in the previous example. Then the dependent task now becomes complete. And we have to, sorry, move that. Oops. We have to propagate up again. So do dependent task.resume. And if that's complete, same problem, should return any of them. Now we can call setObject on the dependent task. So we've got two calls to setObject now. Sorry?
On different instances of the promise type,
Yes.
maybe even different promise types.
They should be, yeah, because they're related to different objects. There's the object that we just had, and then there's the object that depends on that. So let's go to set object, which is just above. Again, we just put it in the cache, and then we look who depends on this object now that we've got it. Go through them, remove ourselves from the dependent tasks container, and then call set dependency. So you can see there's actually a co-recursive relationship between these two functions. So it's the equivalent of that recursion that we saw in the previous example. There's other ways to avoid that if that's likely to be a problem. I think it makes it fairly elegant in this example, though. Most of this is just managing containers. Very little more than that, which is just a bit noisy. So it looks like a lot of code, but there's not really much going on. The important part is that we get to resume the coroutine. Does that make sense? Any questions on that? Okay, then I think we're done. No, we've got a bit more, don't worry. So, we are actually almost done, believe it or not. We looked through all of that, didn't we? What we didn't look at is this batch build task, and the awaiter. But maybe we should look at the awaiter first. Sorry, I'm jumping ahead a bit. If I can remember where I put it. Not that one, that one. Well, first of all, we should go back. So, we didn't really look at this, but we saw it being used. Our dependencies class, the thing that we call require on in the builders. So, that also has this method resolve. And we did co-await dependencies.resolve. And that returns this awaiter, which we just have a forward definition for here. It's just a bit further down, just so it doesn't clutter up the dependencies class. And that's got our three await underscore methods that we saw on the slide. So await ready says, well, actually, if we don't have any unmet dependencies, we don't need to suspend here. But if we do, then await suspend is going to be called, which gets given the coroutine handle, and definition is elsewhere. Let's go to that. And await resume in this case is doing nothing, just logging. But you can put stuff there. So await suspend, we store the awaiting coroutine. Not actually sure we need to store it after all in this case. That may be unnecessary in this case. We often do. And then we take the unmet dependencies. So this bit needs a little bit of explanation. So on the coroutine frame coming in, we've stored the unmet dependencies in the promise type. We're going to get them out of there and store them in our own state. Does that make sense? So we're swapping them so they go away from the coroutine frame and we get them here. Remember I said that the promise type is where we sort of squirrel data away and we can get back to it later. So we'll often put stuff in and bring it out again. This is an example of that. I saw a hand going up a minute ago. Does that answer?
I was just going to say the reason why you would normally store the coroutine handle is because like the awaiter is typically like it's waiting for something to happen.
Yes.
And it's the thing that's going to know when that thing happens.
Mm-hmm.
And when that thing happens, you probably want to resume the coroutine that was waiting for that thing, and you have the handle to resume it.
Yep. So try to summarize that. Thank you for that. I think this is here because at some point I was copying from other examples, and that's what usually happens. Because you'll often the awaiter will be waiting for something. When it happens, it needs to be able to resume the coroutine. In this case, as you saw, we're resuming it from our main loop. So we don't need to store it here. We do need to use it just to get the unmet dependencies out, though. Sorry, who was?
Can we go back to
Ah,
the
yeah, sure.
definition of a waiter?
Yep. Yes, that's the bit I did explain. So the awaiter is constructed with the dependencies object, a reference to it. Yeah, so remember, the dependencies object was constructed on the theoretical stack of our builder, but that stack is actually part of the coroutine frame. So that's going to be sticking around. So we're just taking a reference to it so that we can put the unmet dependencies in there. Sorry, not in there. Halfway around. It comes out of there, goes into the promise type. David.
Where is it that the coroutine machinery is figuring out from a waiter what the type is? It's the return value of waiter. The return value of the waiter is what the
In this case. Yeah.
Thank you.
Yeah, the simplest way is just whatever, I call that, don't have it. It's just up here, that resolve method. That returns the awaiter that we construct with the dependencies. You can use a weight transform, which is on the promise type, is it? I'm looking at you because I know you know. Which just allows you to map the awaiter to something else, which means you can await on something that knows nothing about coroutines. For example, a common example is like stood optional. You can write an awaiter for stood optional just by providing that mapping on the promise type. But if it's coroutines all the way down, then just returning that directly is a simpler way to do it. Starting to run out of steam, but hopefully it's still making sense, at least in pieces. Okay, so there's actually not that much going on, really. It's mostly just shuffling state around. So often you may have to hold on to that handle so you can resume it later. We just don't have to do that in this case. Just to summarize again, I know I've said it a couple of times, but it's easy to lose track with all this. The main thing that this awaiter is doing is, apart from just supporting this interface, is it's taking the dependencies, a reference from taking the unmet dependencies from the coroutine frame and putting them into the promise type by swapping those vectors. So we just shifted that state down. And we'll see where it goes in a second. Right. Losing track. So if I go back to build task, I pointed out the comment earlier. Unmet dependencies from a waiter. Yeah, now we've seen how it gets there. Yeah, you'll often get these like spooky action at a distance type things going on. It's worth putting a comment there to make it obvious where that's going to come from. So I wanted to show you the batch build task. So first of all, we know this is a coroutine because it has co-yield and only co-yield. And it's co-yielding this vector of build tasks. But the return type of the function is batch build tasks. So let's have a look at that. So another promise type, also embedded. Familiar set of methods. Get return object, same process there, nothing unusual. This one is doing suspend never, which I think we did before, yes. So that's about the same. We've got return void instead of return value because we don't have a co-return at all. And we've got the yield value. So when we saw the co-yield, that's going to call here, and it's actually going to await on it. If you think of co-yield as just being co-await promise type dot yield value, that's what it gets transformed to. That's why we have the suspend always. So we can choose whether that yield actually suspends or not by the return type, which may be a runtime thing or it may be a compile time thing. And all we're doing here is just storing the address of that vector up here. So we have a pointer to a vector, which looks very unsafe. Why can we do that? Maybe I should put the question to you, apart from you. Somebody at the back. Yeah, okay.
Yeah. Because that vector that you're getting the pointer to lives in the same coroutine frame as the instance of this promise type?
Yeah, exactly that. In fact, that was the purpose of setting it up this way. Now, it's still a dangerous thing to do. I'm not necessarily recommending this, but you will often do that, because if you want to reach into state within the coroutine body, this is one way you can do that without the overhead of a lot of copying. But do be careful with your lifetimes. It's very easy to screw them up. So yeah. Yeah.
Is this the reason, or one of the reasons why the coroutine does a co-yield rather than a co-return?
Yes, that is the reason. Well, yes. So I believe, and I could be wrong, correct me, that when you do co-return, even if you're doing suspend always, which means the coroutine will still be around in a suspended state, I think all of the internal variables have got cleaned up at that point. That's true, isn't it? Yeah. So if I'd done a co-return, then yes, the vector would have gone.
The destructors fire on co-return.
Right.
So you co-yield and always suspend it, never resume it, but you did the yield instead, just so the frame,
Yeah.
the variables inside the frame stay.
Yeah, exactly. So it's a little bit of an abuse. David.
I was just gonna, I guess, clarify. So this, you wouldn't consider this to be best practice use of coroutines, right?
Well, I'm relying on the fact that currently there are no best practices. It's a bit of a Wild West. But if there were best practices, which are sort of emerging, then yes, I would say probably not. But I don't know any other way to efficiently get at internal state of the coroutine if that's what you need to do. Yeah. Yes. Might even be the best way here, because I don't think you need it after this point. Yeah, I should probably rewrite that. I'll have a look at it anyway. Good point. But for now, at least we've got that reference onto the pointer into the coroutine frame. So that's yield value. So in the same way that we saw a co-return called return value, and then we just squirreled it away in the promise type, same thing here. Same job. We're not actually returning it anywhere. We're just storing it. And later, in the batch build task, we can access it this way, get subtasks, which just reaches into the promise and returns that pointer. That does mean, and this is one advantage maybe to having the pointer, is initially we know it's null. So at this point you can call it out and you can test whether you actually got them or not. Otherwise this looks very similar. Move only again. Can't remember why we need to move it now. But same destructor. And I think that's all there is to it. It's a slightly simpler one, just has that bit of a wart around the pointer to the vector. And the fact that we are relying on it just being suspended in memory until we're finished with all of the others. So it's more of a way to get access to the individual coroutines that are loading the objects and hold them in memory. Does that all make sense? Oh, there is an awaiter for it as well. Here. So we pass the subtasks in when we await. We only suspend if we had any subtasks. But we don't actually need to do anything in await suspend because we're never actually going to resume.
This awaiter is totally unused, right?
I was actually thinking of that as I was talking it through. It may be left over from an earlier iteration. So maybe we should see what happens if I delete it. Or at least comment it out. Because I'd rather give you the right information. Okay, yeah, we can ignore that one then. I think I did need it at some point. I think I may have been experimenting with using co-await instead of co-yield. That sounds about right now. Thanks for pointing that out. Which means, I think, we have actually covered it all. I may have missed something. Just a bit at the end where we pull out all the objects from the cache so we can return it. Nothing fancy about that. We can run it. And completes in approximately the same time as the previous batch version because it's dominated by that false database latency. I was going to do a version where I took that out so we could compare the actual runtime costs of the coroutines, but I'd need to set up a proper benchmarking tool for that. So it's an exercise for the reader. But if we go back to this, I think the only thing that really stands out here as not being neater all round is this ugly loop. Here, there seem to be more moving parts than we had previously. But I think these bits are simpler because some of that logic's moved out. And certainly the builders themselves are much more expressive. So first of all, before we go back and look at how some of these things piece together, any thoughts on the solution we've ended up with? A few. So, Andreas.
So you're still not doing the asynchronous waits, right? There would be further optimization if you like the sleeps themselves. You wouldn't block on them, but also hide them away like in an asynchronous call, which could also be done.
So the question is, this is still not a fully asynchronous version. It's asynchronous in that we are doing bits and then going off and doing other stuff and then coming back, but all on a single thread at the moment.
And you're still having to wait for the full sleep without being to do useful stuff in between, right? Like the optimization that we're doing is still just the batching, as we did in the second version, and like the next step will then probably be to...
You mean while we're waiting for the database, we're not doing anything? That is correct, yes. And there's probably not a lot that we could be doing here in that time, just because the building of stuff is a tiny fraction of the time.
But you could start a second database query.
I think you need the result of the first one.
Yeah.
Oh, that's the problem.
But what you could do is you could create, I've got a single resolver here. You could create several resolvers and give some objects to one, some objects to the other, and then stagger them. But that's not really making that much use of the coroutine machinery at that point. This is mostly just so that we can interleave the database reads and the builds independently. David.
My reaction to this is that we added like hundreds of lines of extremely complex code to get these 10 lines over here looking pretty nice. And,
Yep.
and I don't know how that's going to be really practical in a normal engineering environment. People use coroutines and solve this kind of problem.
So yeah, to repeat the comment, we seem to have added hundreds of lines of code just to save a few lines of code or make a few lines of code look more elegant. And is that really practical? Part of the problem is I wasn't able to get my two examples close enough that we could compare them like for like and see, did we actually lose lines of code or have we added any? I think we actually just traded some for some other. So it's not necessarily more, but more of it has gone into the boilerplate. And I think that's a good thing, because that boilerplate can now potentially be either reused or we can start using third parties or standard facilities as they become available. Now, in this case, our task was fairly custom, so I'm not sure how much reuse we'll get. But in general, yeah, we can start to rely more on pushing the boilerplate parts down into reusable facilities. I think the main loop that's outside of the tasks and the awaiters, although it was a big loop, was actually packing in quite a few bits from different parts of the code base before. So that's why it's a shame I couldn't compare it like for like, but I think it's not more complex. Yeah.
Yeah, I think the benefit is that you have a more streamlined program logic right now. So I didn't expect any speed up because in the essence you do the same work, just in a different order. You didn't use parallelism or something like that, but with this more streamlined version, you now have a better way to reason about how to parallelize on it.
Yeah.
And you can fire out your coroutines and they work parallel.
So to summarize the comment, you wouldn't have expected any speed up because we're not really taking advantage of any forms of parallelism or anything like that. So absolutely,
You could wait on a database call and then fire out another thread. This would be enough.
Yeah. One thing I should have really emphasized earlier is if we look at this fobjects folder. Actually, I'll put a few more in there. We've got a handful of objects that need building here. In a real quant library, there will be certainly hundreds of them. Each one of those will have one of those few lines of code to build a code. And it really multiplies out, believe me, I've done it, when you have to do that part in a more verbose way. So once you add in more of these, then it really tips in favor of, yeah, let's add a bit more boilerplate here if we can streamline those few lines of code in hundreds of places. That's really what this exercise has been about, rather than raw performance so far. Ezra.
If you can jump to any await suspend function that you had, if you can pull up an await suspend function.
The call to one.
The definition.
Sorry?
The definition of an await suspend function. There was a parameter that was called new suspend coroutine or new. There was a coroutine handle being passed into this await suspend function. So.
Oh, right, in the awaiter.
The awaiter, yes.
You got rid of that later?
What did I do with that? Let's find it again. This one?
New awaiting coroutine. Okay, so this function can only be called from a coroutine because with co-await, right?
Yeah.
So that means there are two coroutine handles we are considering. One that is about to be suspended, and one that is about to be resumed.
Yes.
Which one is that?
This one is the one that's being suspended.
Suspended. Okay.
Yeah.
The coroutine that contains the co-await expression.
Yeah. So I think what you're leading up to is something I haven't really got into, which is if you've got like a sequence of coroutines that need to be executed in sequence, your awaiter can actually have the one that needs to be resumed next here. So we can actually transfer from one to the other, rather than going back out through the whole machinery and back in again. So process called symmetric transfer. Was that what you were going to be leading up to?
I don't know. So
Okay.
Yeah, like I think await suspend is allowed to, instead of true or false, do or don't suspend me, it also has the option of returning a coroutine handle,
Yes.
which means suspend me and resume this guy.
Yeah. That's the bit that I was missing. Thank you. Yeah, so with a lot of these functions, because they're not like virtual interfaces, there's different signatures that mean slightly different things. So await suspend is the main one. It has 3 different return types. I think the other one's void, isn't it? Yeah. So it can return void, bool, or the coroutine handle. And if it returns the coroutine handle, that's the one to resume on next. And that allows you to just save some space and time. But don't ask me to get into the details right now off the top of my head. But maybe you could if somebody's interested. But does that answer your question at least? Thank you. Okay. Really running out of air. So, do we have any more questions? Do you want me to show you anything again? Yeah.
Having now gone through all this, do you find yourself reaching for coroutines to solve any particular class of problems? Like when should I, what should I see that should make me think coroutine? This is the fundamental.
So first of all, I should point out that you heard the term the curse of knowledge. That once you know something and become very familiar with it, it's very difficult to remember what it was like not to know it. So I often try to do talks on things that I've just learnt so that I can try to give you some of that benefit of the pre-curse of knowledge. Which means I've only really learnt a lot of this stuff while preparing for this talk. But that said, obviously I knew about coroutines and basically how they worked before. And the one thing that kept coming back to me was this would be a perfect solution to this particular problem that I had. So yeah, if I was writing this code again, I would reach for a coroutine to do it. Now I've got better understanding of all the machinery, I've got a better idea of how I can apply it to other problems. Right now, it's maybe a bit heavyweight for some of the simpler things because we don't have the libraries. But when we get the libraries, I think that'll open up a lot more opportunities. There are third-party libraries that maybe will cover some of that, but then you've got another dependency. So I'm not quite at the point where I'm looking for opportunities to use it just yet, for me at least. I don't know if anybody else has different experience there. Andreas?
Maybe one way to put it is that they are useful when you're in the middle of doing something, you would like to do something else, right? Like as we're doing, like we're in the middle of constructing this object, and suddenly we realize we need a dependency to continue, right? So we need to stop what we're doing right now, like stop in the middle of the construction and then get this dependency, right? And if you do this with the traditional methods, then you often get like very complex and sometimes weird control flow patterns. And coroutines allow you to streamline that. I think that's the best way that I reason about.
Yeah, that's a good comment. I would still say that, again, with the smaller problems, the amount of boilerplate you have to write could be off-putting. But, of course, over time you'll start to build your own library of helpers as well, I would imagine, if you're not using something third-party. Really hope that we do get those generators in C++23 because that's something that can be really nice in a lot of circumstances. It's nice and simple. And with generators, I should probably explain what generators are. Really, all they're lazily generating sequences. So you can just iterate over them, and every time round it will generate a new value. Generators with coroutines, if you've got a library facility to handle the boilerplate, then you can just concentrate on a very simple function that generates the coroutines and nothing else, and get all of the benefits of the rest. At least that's the idea. If you've used equivalent things in, say, Python, you probably know how that looks. With the async tasks, there's always going to be more complexity anyway, and a bit more variety. So that one's a bit more of an open question, but generators should be like an easy win once we get the library support. One other use case for generators that I've been thinking of for a couple of years now, and I wanted to get this experience so I could actually see where it's really going to work, which might be a bit unusual, is a test framework. So with a unit test framework, you have to start executing your test code, but then potentially call back into the test framework machinery to do things like, report results and check configuration and that sort of thing, which you can do without coroutines. But I've been thinking maybe a better way to do it, because it also means you can do early returns from a test without having to throw an exception, which is the current mechanism of choice. So that's something I have on my list to experiment with that you may not have thought of otherwise. I appreciate I showed you all of this sort of a low-level detail perspective. Is there anything else that might help to piece bits together? Because often that's the problem. So we have a room full of coroutines experts now. That's excellent.
For the next 10 seconds.
Because if not, I think I am pretty much done with material. I can put that back up because I think it's worth mentioning again. These are some other places to go, not exhaustive, but useful, that I've used. I should maybe also mention Nico Jasutis' book that's still in development. The coroutines chapter is also still in development. But last time I looked, he got some pretty good coverage of at least the promise type, and is actively working on it. So that will be another resource that I would tentatively add up there, even if it's currently suspended. So any other questions before we wrap up? Yeah.
I remember there's a place where you use basically code yield to return a value into a co-return. Let's say my code reviewer thinks this is a bad idea and I want to use co-return instead. Is there any particular change, like what type of change do we need to make, and why, I guess, do you still use code yield?
Yeah, so I may have confused things a bit with my abuse of that yielding coroutine. Usually you would use co-yield if you want to return more than one value, like in a loop or several over a period of time. Whereas co-return is like the final thing you want at the end. So obviously if there's only ever one thing you want to return, it could be a choice. Could it be a co-yield or a co-return? Co-return is probably usually the more obvious choice because it's more expressive in terms of the intention. But I chose to use co-yield there so that I could keep all of the variables in the coroutine frame and rely on them being in memory. So I was cheating a little bit, and that may have confused the issue. But they're very similar, and they both push values into the promise type that you can get at from outside. Just that one of them also signals the end of the coroutine.
Coroutine destroys, or return destroys activation frame.
Yes, yeah. It destroys the sort of the local stack of all the variables. The coroutine frame is still there until it's destroyed via the handle.
The state is
Well, yeah. We didn't really get to coroutine cleanup so much because it can get tricky. If you have in the promise type final suspend always, which most of the time you should, then the coroutine is still there in a suspended state. But all of the local variables in the coroutine body have been destroyed. But the promise type, I think, is still there. So that's like a halfway house. If you've returned suspend never from final suspend, then as soon as the coroutine runs off the end, it will get destroyed. And you may have lost some state that you still needed access to, which makes it quite tricky to manage.
also the standard flow is the current state is destroyed when the control flow flows off the end, or the destroy member function is called. So it seems like you don't have to call destroy if you let it to on its own terms, and it will destroy the entire frame. That's what it applies to me.
You actually, if you call destroy after it has flown off the end, it's only for anything you will get the same forms.
Yeah, so what if you never call destroy, but let it fall there?
You can do that, yes. It will destroy everything.
It will destroy everything,
Yeah.
including the allocation of the frame.
Yeah, exactly. It will clean up itself, but like managing lifetime in this case becomes super messy. Because like you
Well, you will only do that in the structure, in the generator that, well, no, and when it decides, it's not, the generator you destroy.
You would use it for one-shot function or something.
Yeah, if you like a one-shot or two-shot functions, after that you let it fall out, and you count shots yourself.
Where in your main program you have like this step, and then forget about
Right,
it.
yeah. Yeah, if you know how many times you're gonna call it, yeah.
So to summarize,
You don't have to destroy it if you let it.
Yeah.
And you do it like this, you don't have-
so to summarize, the lifetimes get messy. I think that was the key point.
There you go. Good job.
Yeah. No, but certainly if you do the final suspend never, it does get tricky to reason about. And I can't remember the details off the top of my head now anyway, so I defer to what the audience has been saying, and yeah.
I just want to add one more resource. If you know Raymond Chen's Microsoft
Yeah.
blog, The Old New Thing, he has a really great series of articles about coroutines that additionally go into some of the implementation details. And so if you're finding this to be a little too magical, you might find that particular resource helpful.
Yeah, so to repeat that, Raymond Chen's The Old New Thing has a series of great nuts and bolts articles on coroutines, mostly from the perspective of the way Microsoft do it, which sometimes becomes relevant, but yeah. Any others? Or we can do an early return. Thank you very much for putting up with me.